Okay, and now let's really emphasize a key point about the resonance hybrid. So when we're talking about the resonance hybrid, or the actual structure that we observe is a weighted average of all resonance structures based on their contributions. And as we've discussed previously, just like Lewis structures, we can assess the contribution of a resonance structure by looking at, for example, whether the octet rule is satisfied. That's first and foremost. Whether we are minimizing formal charges, that is almost equally important. The octet rule wins out when you talk about carbon-centered species. So in general, for carbon, you're almost always going to want to satisfy the octet rule. Formal charges come into play primarily when you have species like chlorine, bromine, boron, sulfur. So species that exhibit either expanded octets or incomplete octets, the formal charges really start to play a bigger role. Now, in general, you want to place negative formal charges on the electronegative atoms and positive formal charges on less electronegative atoms. You can also call these electropositive atoms. Finally, you in general want to place opposite formal charges on atoms that are adjacent, that are opposite to one another. So, for example, when we looked at acetate, we were able to quickly see that the two major resonance structures that we can draw for acetate anion are any of these resonance structures. So structure on the left, structure on the right. Is there any preference? Are any of these structures preferred over the other? Is there any difference in how we have placed our negative charge? Is there any difference in the octet rule? No, right? They're almost functionally identical. In the first example, we have a negative charge on oxygen. In the second example, we have a negative charge on, shockingly, oxygen again. So then, following these criteria, both of these two structures are equal contributors. So as a result, we'd expect our resonance hybrid to be a straight average between these two structures. So then, as a result, if we were to draw that out, if we were to draw out our resonance hybrid, so we definitely have a single bond between our carbon and our oxygen. And now, instead of having a double bond shared between a single carbon and a single oxygen, our double bond electron density is instead spread about all three atoms involved in resonance. So instead of being a double bond, what would be the best descriptor of our carbon-oxygen bond? What would be the best descriptor that we can think of? Instead of a double bond, it would be, but let's put some numbers to it. So instead of a single bond, 1.5, exactly. So this would be closer to a 1.5 bond. And the way that we got 1.5 bond is that we have a double bond. So in essence, we have a double bond. So the best way to think about it is in one resonance structure, we have a single bond. In the second resonance structure, we have a double bond, right? So if we take the average, 1 plus 2 divided by our number of resonance structures, which is 2, gives us about 1.5. Does that method of estimating bond order make sense to everyone? You take the bond order found in each resonance structure and you average it together. And the way that we represent this 1.5 bond is typically with a curved line. Now there's one other thing that we have to appreciate in this resonance hybrid. What charge is being distributed about all of these oxygen atoms? Negative charge. So we put a minus sign. Okay. So this hybrid is our best picture of the actual bond length, strength, and charge distribution in our molecule. Does that make sense? So what I want you to consider, what I want us to consider now is we're going to look at two different ketone derivatives, the first of which is an acyl bromide, And what I want us to think about is, why are acyl bromides so reactive at this carbon? Why is this carbon relatively reactive? And what we're going to do is we're going to draw out some resonance structures, and we're going to see how our charges are distributed. Okay, so with that said, following our rules from last time, we can use arrow pushing method, and we can take electrons found in a lone pair adjacent to a double bond, and we can push those electrons down to form a new double bond and a new lone pair. So we draw our arrow from the lone pair to the newly formed double bond, and then up to our oxygen atom. We are forming a double bond and then breaking a double bond in the process. Does that make sense? Okay. So then we have the following structure, which should immediately be setting off some red flags to some people. I haven't drawn my formal charges. Let's do that really quickly. What's the formal charge on oxygen? What was that? -1, exactly. And what's the formal charge on bromine? +1. Yep. An important thing when thinking about resonance structures is your total charge will not change, right? If you're just moving around your electron density, the total charge of your molecule by definition cannot change because our total number of electrons has not changed, right? So then, what's another potential resonance structure that we can draw? What's another potential resonance structure that we can draw? So we have electrons found in a double bond, right? So can we move those electrons found in a double bond to any of the atoms involved in our double bond? Yeah. So if we had to pick, which atom is more electronegative, carbon or bromine? Bromine. So where would we like to push electron density onto? Bromine. Okay, so I'm going to draw my curved arrow going from the double bond to bromine. Okay, and key thing, you want to draw your arrow with double-headed, not single-headed. Single-headed refers to radical electron pushing, which we'll talk about later. Okay, and that gives us the following resonance structure. So now bromine's relatively happy, but lo and behold, we have a bit of a problem now. Let's take a look at our formal charges. The formal charge on oxygen is -1 still. What has happened to the formal charge on our central carbon? It only has 3 bonds to its name. Positive, yep. And let's write this as +1. Okay, now, looking at each of these structures, if we had to assess using the octet rule and formal charges, which of these 3 structures is the largest contributor? Which one satisfies the octet rule and has the smallest formal charges? The structure on the left, middle, or right? Left, by far. The structure on the left is substantially preferred. Would someone like to provide me a reason why? What's the hallmark of this structure that makes it so good? Yep, 0 formal charges, and is the octet rule fulfilled? Yes, so this would be number 1. Now, if we had to rank number 2, what would be the second most favored structure? The middle one, right? And the reason being, even though it has formal charges, and even though those formal charges are not great, does it still fulfill the octet rule? Yep. Does it place the negative charge on the more electronegative atom? Yeah. Oxygen's more electronegative, so it's not unreasonable to put a negative formal charge on oxygen. This last structure breaks the octet rule, which isn't completely damaging, but nonetheless makes it much less favored, and its formal charges aren't the best. They're okay. This motif is a typical resonance structure that you'll see in any keto derivative, be it an amide, an ester, a ketone, the super common resonance form. And this really explains why, if we think about reactivity, this central carbon with this positive formal charge found in a lot of these resonance structures is particularly reactive. Now, What I want us to consider next is an amide. Now, amides are quite special. What I want you to do is to draw the resonance structure for an amide, draw at least 2 resonance structures, rank them in terms of their relative contribution, and then what I want you to do as an exercise is compare the second contributor for your acyl bromide to the second contributor for your amide, and tell me which resonance structure has greater sway in the hybrid. Which one is a greater contributor? Using our formal charge rules. So I'll give everyone a moment to do that, and then we'll come together to discuss. Yep. Perfect. Yep. But make sure to draw your formal charges. Yep. Perfect. All you have to do now is fill in your formal charges. Yep, exactly. Yep. Perfect. Even the formal charges are filled in. Yep. Yep, looks good. Yep, looks good. Yes, looks good. So now let's talk a little bit about, I saw the major contributing resonance structure drawn almost immediately. So let's talk about that. So first things first, we kick down our lone pair electrons to form a double bond. And as a result, we break our currently established double bond to generate a new lone pair. That in turn gives us the following resonance structure. Now, we have to fill in the formal charges for this structure. What's the formal charge on oxygen? -1, yep. And what's the formal charge on nitrogen? Positive. Now, if we had to do a comparison between the acyl bromide resonance contributor and the amide resonance contributor, which of these 2 potential structures is more favored according to our formal charge rules, according to the octet rule, etc.? The lower one. And would you like to provide a reason why?
The main reason is because nitrogen is less electronegative, so it's more likely to have a positive charge.
Exactly right. Exactly right. So if we focus on nitrogen versus bromine, nitrogen is less electronegative. It prefers and it can more easily accommodate a positive formal charge. And as a result, this bottom resonance structure has a greater contributor to your overall resonance hybrid. We'll talk about the implications of that in a moment. Now, for our last throwaway contributing structure, you can draw a structure that violates the octet rule, which looks a little bit like this. And let me fill in the formal charges. Okay, now we've established that this resonance structure is a major contributor, right? It follows the octet rule. Its formal charges are present, but they aren't particularly bad. Nitrogen is electropositive. It can accommodate a positive formal charge. So one of the consequences of this depiction of the different resonance structures is when we draw out our resonance hybrid, would we expect this resonance structure containing a carbon-nitrogen double bond to have an influence on the carbon-nitrogen bond order in our hybrid? Would you expect there to be some double bond character in our hybrid structure? Yep. And would we expect it to be relatively substantial, since this structure is relatively good according to our assessment of formal charges, octet rule, etc.? So one of the consequences of this is, in biology, when you look at amide bonds are not quite three-dimensional in terms of character. Instead, amide bonds are flat. So you can best describe the distribution of electron density in an amide bond as very similar to your acetate anion, where instead of having a strict carbon-nitrogen single bond, instead we have a bond that is approximately, but a little bit less than 1.5. So the reason why it's a little bit less than 1.5, but it's still quite stronger than a single bond, is although this is a relatively major contributor, it is not an equal contributor to this first structure, right? Because the first structure is a little bit better, right? Has minimized formal charges, it fulfills the octet rule. So as a result, and the key takeaway from this is amides are flat. So amides are flat. And the carbon-nitrogen bond is strong. So amide bonds are infamously hard to break, and it's a result of this resonance contribution. Does that make sense? So let's get some more practice in drawing resonance hybrids. So another classic system where you'll see a major contributing resonance hybrid is when you start looking at enolate. So this structure is known, or this anion in particular, is known as an enolate. It's a carbon-centered anion adjacent to a keto functionality. Now, if we think about our formal charge rules, a major resonance structure is more favorable if it places negative formal charges on electronegative atoms. So looking at these two potential resonance structures, which of these two resonance structures is preferred? Which one places the negative charge on the more electronegative atom? One on the right, exactly. And this is often why when we think about enolates, we're really looking at the enolate geometry, the geometry with respect to the double bond. The double bond character is quite substantial for an enolate. So what I want us now to do is to take a look at urea or a urea derivative and assess and draw out resonance structures for this compound and identify the largest contributing resonance structures. Okay? And try to rank them in terms of their contribution. In some cases, you can end up with multiple structures that are equal contributors. So take a few moments to tackle this problem, and then we'll come together to discuss. Everything going okay? Everything going okay? Yeah, that's good. And will there be any difference between those two structures in terms of the two on the bottom in terms of contribution? Or yeah, that's good. Yeah, that's good. Yeah. Looks good. Oh, just make sure to check your formal charges that are in the structure on the farthest right. Oh, yep, that looks good. Yep. So let's now come together to discuss. So using arrow pushing notation, we have lone pairs adjacent to a double bond. So we can kick these lone pairs down. That results in our double bond breaking, and we can end up drawing a new resonance structure. So probably one of the most common resonance structures that you see, very similar to our amide example, is a resonance structure containing a carbon-nitrogen double bond. Now, we do have to be very careful that we assign our formal charges properly. So what is the formal charge for our double bonded nitrogen? If it has a nitrogen with four bonds, +1. What about our oxygen atom? What's the formal charge of oxygen? -1. Okay. There is another potential major resonance contributor that you can draw where you kick the nitrogen lone pair down and break the carbon-nitrogen double bond. That in turn gives you the following resonance structure. So we have NH2. Let me draw the hydrogens on the other side. Yes, exactly. And it doesn't matter in terms of sequencing because when you're drawing resonance structures, these are all just pictures to represent distributions of electron density. In reality, our actual structure is an average. So it doesn't matter where you start. Okay, so now if we compare these two major structures, is there any difference in terms of their contribution to their overall resonance hybrid? Is there any difference between these two resonance structures in terms of contribution? Any major difference that you see? No. So these two structures, these two resonance structures are equal contributors. Okay. Now, what is the largest contributor to our resonance hybrid? Which structure minimizes formal charges, follows the octet rule? The one on the left. So if we had to give a ranking, this would be number 1, while these two structures would be tied for number 2 in terms of their contribution. However, just like amides, ureas, the geometry centered around nitrogen is planar. There's a lot of double bond character in that carbon-nitrogen bond. Does that make sense to everyone? So now let's try to take this a little bit further and let's apply to a few more examples. So resonance plays a really large impact on the hybridization of atoms. So for example, when we think about the actual hybridization and geometry of atoms in a structure, just like our bond order, it's going to be the weighted average of all of your resonance structures. The same is true for your bond angles. So the bond angle that you observe for a given bond or set of bonds is a weighted average of the bond angle found in each resonance structure. So we discussed amides at length. So I'm going to draw us our stereotypical amide. So we have an NH2 and a carboxylic acid. That looks a little bit like this. Whoops. Now, as we discussed previously, there is a major contributing resonance structure for the amide functionality. And we can draw that by pushing our arrows from the lone pair down and kicking our double bond up. And that gives us the following contributing structure. Now, a consequence of this resonance contributor is if we look at the hybridization, of our amide nitrogen. So this is +1, -1. We've seen these formal charges before. My question to all of you is, what is the hybridization of this nitrogen in this resonance structure? If it has a double bond and 3 single bonds, sp2, exactly. So in this resonance structure, this nitrogen is sp2 hybridized. And as a consequence of that, in our resonance hybrid, this nitrogen will have a large amount of sp2 character. Is there another atom in this molecule that will have a large amount of sp2 character besides the carbon, of course? Following this idea, if we have a lone pair adjacent to a pi system, we can generate a resonance structure where our nitrogen atom has a substantial amount of sp2 character. Now, to answer this question, can we just try drawing out more resonance structures? Would that be a valid approach? Yep. So let's do just that. So we've kicked down the lone pair on nitrogen to form a double bond. Does oxygen also have a lone pair that's raring to go? Yep. So we can draw out a resonance structure by kicking down this lone pair and kicking up our double bonded electrons. And that in turn gives us the following resonance contributor. Now, if we had to take a guess, looking at this structure, I'm going to assign the formal charges for us just to expedite this discussion. If we had to compare these two resonance contributors, is the structure on the bottom with a positive formal charge on oxygen, is that as significant of a contributor as the structure that places a formal charge on nitrogen? No. And the reason being, is oxygen more electronegative? Yes. So then, even though this structure is relatively minor, in this resonance structure, what is the hybridization of this oxygen atom? sp2, right? So then, as a consequence, in our resonance hybrid, what will that oxygen have a large amount of sp2 character? Yes. So then, even though our predicted hybridization for this nitrogen and this oxygen would be sp3, in reality, the geometry and bond angles more closely match that of an sp2 hybridized atom. So resonance, in turn, can affect the hybridization of your atoms in your structure, and it affects the geometry. So, as a general rule, if your lone pair is adjacent to a pi system and is able, geometrically allowed, to place that lone pair in an overlapping p orbital, then the hybridization will be adjusted to be sp2. So that way you can get conjugation and delocalize this lone pair through resonance. Does that make sense to everyone? Now, just to be 100% clear here on what's going on, why would we need an sp2 hybridization for this kind of conjugation? What's the definition? What's the principal overlap that's responsible for resonance? So let me show you. So looking at our carbon-oxygen bond, we have a double bond, and that is a pi bond, which involves the overlap of parallel p orbitals, right? This is our pi bond, right? So in order for us to delocalize our lone pairs into this pi system, in order for us to overlap with this pi bond, where does our lone pair need to be? What orbital does our lone pair need to be? P orbital, exactly. So for this nitrogen atom will adopt an sp2 hybridization, and the lone pair will be kept in a p orbital. As a result of this, the lone pair can participate in conjugation and be delocalized throughout this pi system. So that's why we see these hybridization effects. Not only because we can draw a resonance contributor with an sp2 hybridization, but in order to delocalize this lone pair, which is a very favorable effect or event, we need an sp2 hybridization. Does that make sense to everyone? Okay, so there's energetic benefit to conjugation, and that's why if you have a lone pair adjacent to a pi system, the hybridization of the atom adjacent to that pi system will typically be sp2, or a hybridization that allows it to have a p orbital conjugated. Okay, now you may say, what's the point? Well, resonance has a profound effect on your bond length, strength, and your molecular geometry. So for example, when we look at the bond angles involved in this overall structure, if we look at the bond angle centered, for example, in our amides, if we wanted to predict a priori, what would the bond angle around nitrogen be? Considering that we know that the amide nitrogen has a large amount of sp2 character, what would we expect the bond angle to be around that nitrogen? 120 degrees. So this is why you always need to keep an eye out for resonance effects, because it directly impacts your observed bond angles and your observed bond strength. Everyone clear on that? Okay. So what we're now going to do is we're going to take a little foray into slightly more complicated systems and start drawing resonance structures to start to get a sense of predicting reactivity and properties. So, as we've already discussed previously, in general, the hybridization of atoms participating in resonance is generally going to be sp2 or sp because they must have a p orbital to interact with our pi bond or pi system. So, what I want us to do now is to take a look at some structures and indicate the hybridization and geometry of each atom in the structure. So I'll start us off and we'll look at a classic acrylate derivative. So in this case, what I'm going to do is I'm just going to first look at the structure as it is and then keep an eye out for potential resonance effects. So starting off, looking at these two carbon atoms, what is the hybridization of these two carbon atoms? sp2. Yep, sp2. And as a result, they'd have a trigonal planar geometry. Likewise, we can also assign an sp2 hybridization and a trigonal planar geometry to this central ketone carbon. Now, looking at this methyl substituent here, what is the hybridization of this carbon indicated, of a methyl carbon? sp3. Yep. So, and it would adopt what kind of geometry? Tetrahedral. Now, where things get interesting is when we look at this oxygen atom here. What is the hybridization and geometry of this ester oxygen? So let's think, accounting for resonance effects. sp2. Yep, it's quote unquote sp2. It's not quite a full sp2 hybridization, but it's very close to sp2. And if we think about this bond angle, and if we think about this geometry, what geometry best reflects this sp2 hybridization? Yep, 120 degrees. So it's trigonal planar. And just to be specific, it's trigonal planar with a bent variation. The reason why it's bent is because we have a lone pair instead of just 3 bonds. Does that make sense? Okay. Yes.
And so we're taking the oxygen sp2 because of the.
Yes, exactly. In order for the lone pair to participate in conjugation and to be delocalized throughout this pi system, it needs to be in a p orbital. And the only way for us to have a p orbital present with a lone pair is to adopt an sp2 hybridization. Does that make sense? Perfect. So what I want you now to do is to take a look at the following structure, assign the geometry and hybridization of each atom in the structure, and make sure you are accounting for resonance in your assigned geometries. Any questions? So it's bent because instead of having 3 bonds, it has 2 bonds and a lone pair. And the lone pair distorts the geometry. That's it. Yeah. So it's bent is it contains a lone pair, so your geometry gets distorted. And this is a technicality. We only assign hybridization for oxygen atoms with more bonded to more than just one atom. Though it's not incorrect to say it's sp2 character, it's just hybridization literally so that you get multiple bonded atoms. Yep. Looks good. So let's do some hybridization assignments. So first and foremost, let's take a look at these 3 carbons. What is the hybridization of these 3 carbons? sp2. And what would the geometry be? Yep, trigonal planar. This methyl, of course, adopts what hybridization? sp3, yep. And that involves a tetrahedral geometry. Now, let's take a look at this oxygen. What is the hybridization of this oxygen if it wants to conjugate its lone pair, if it wants its lone pair to participate in delocalization? sp2. So as a result, the geometry centered around this oxygen would be trigonal planar bent. Just to be 100% clear, if we look at this oxygen shown here, we only really hybridize if we're bonding to more than just one atom. This oxygen can form a double bond, hold its lone pair in unhybridized orbitals. You can technically say that this oxygen is like sp2-like, but is technically unhybridized. Don't worry too much about that detail. Looking at this carbon shown right here, what is the hybridization of this carbon? sp, yep. Has 2 sigma bonds and 2 pi bonds. Would it really be appropriate to label the hybridization of this nitrogen as sp, or can we just say it's unhybridized? Can we form all the bonds that we need without hybridizing? Yeah, we can, but it's often useful to think about this nitrogen as sp-like in terms of the energetics of that lone pair and the relative reactivity of that lone pair. Any questions on this example? Yes?
Why is it called sp-like?
Because technically you don't have to formally hybridize to get that given bonding arrangement. So if an atom doesn't need to hybridize in order to accommodate bonding, it won't necessarily hybridize. But for the purposes of thinking about the energy of that lone pair, the lone pair on this nitrogen is very similar to the lone pair on other sp hybridized atoms. And that'll be important when we talk about acid-base chemistry and assessing the relative energy of lone pairs in conjugate bases. Does that make sense? Okay. So let's keep going now. And let's talk about resonance and bond order. So when we think about calculating bond order, accounting for resonance, to calculate the average bond order for a given bond, what we need to do is we need to draw all of the major contributing resonance structures. We determine the bond order in each structure, and then we add together the bond order in each structure, and then we divide by the total number of contributing structures. So not all resonance delocalized bonds are the same bond order. So let's take a look at NO2 minus. Let's take a look at NO2 minus. So counting up our electrons really quickly, we have a total of 18 electrons to work with. And what is our central atom going to be? Nitrogen, yep. We're going to surround it with 2 oxygen atoms and form 1 bond each. So that gives us 14 electrons to work with. In our next step, we're going to place lone pairs on each of our atoms. So where do we start placing lone pairs? Oxygen. The reason why we have to do this structure from scratch is because it does not match any of our functional groups exactly. Now, where do our last 2 electrons go? Nitrogen, yep. Okay, and now have we fulfilled the octet rule on nitrogen? No. So now let's convert a lone pair into a double bond. Now we've fulfilled the octet rule. Let's do one last thing and let's assign formal charges. So we would have a -1 formal charge on the leftmost oxygen. Perfect. Can we draw a resonance structure for this molecule? Yes, we have a lone pair adjacent to a pi bond or pi system. So what lone pair are we going to kick down? Oxygen. Yep. So we're going to take this lone pair on oxygen, we're going to kick it down, and our double bond in turn breaks. And that in turn generates the following major contributing resonance structure. Okay, now we have our negative formal charge. Now we have our negative formal charge on the rightmost oxygen. Are these structures equally contributing? Is there any difference between these 2 structures? No. So then we can now, let's take a look at this specific nitrogen-oxygen bond. And let's count our bond order in each of these structures. So in structure 1, what's our bond order? 1, okay. In structure number 2, what's our bond order? 2. We then divide by our total number of contributing resonance structures, which would be 2, okay? And that in turn gives us a bond order of 1.5 for our nitrogen-oxygen bond. So it's not quite a single bond, not quite a double bond. Now, let's compare this to the carbon-oxygen bond order in carbonate. So let's take a look at CO3 2-, and let's draw out the Lewis structure and the contributing resonance structures. And what I want you to be able to tell me is the carbon-oxygen bond order. And just as a hint, you'll need at least 3 resonance structures for this. Everything going okay? Everything going okay? Oh, and it's 2 months. Yeah. Oh, and just it's CO3 2 months. Yeah, you already have it drawn correctly. Yep. Yep. Everything going okay? Yep. I would recommend drawing your structure with a little bit more respect for the geometry, which is streamlined. But otherwise, it's fine. Everything going okay? Everything going okay? Yep. All you need to do is fulfill the octet rule. Oh, almost perfect. It just needs to fulfill the octet rule. This carbon. Yep, perfect. Everything going okay? Okay. Oh, and it's 2-. Yeah.
Saying this is 2 minutes, and this is what
Yep.
I'm getting over.
Yep.
I was like, this doesn't make sense.
Yep. Everything going okay? So what's the average bond order? need to draw the resonance structures to answer that. Mhm. Yep, exactly. So I've seen a lot of reasonable solutions so far. So what I'm going to do is I'm going to first generate our Lewis structure, and then really the Lewis structure is our starting point for all of these discussions. So you want to be able to quickly generate Lewis structures. Okay, so here's our Lewis structure for carbonate. Now let's focus on drawing out resonance structures. So we have these lone pairs adjacent to our pi bond or our pi system. Can we generate a resonance structure via arrow pushing? Yeah. So the first resonance structure, we kick the lone pair down on the rightmost oxygen, and our double bond is broken in the process, and that in turn gives us the following resonance structure. Okay, we can draw another valid resonance structure. We have a lone pair adjacent to a double bond. Let's try not to regenerate this structure on the left. So where can we kick a lone pair down from? Yep, the oxygen on the left. Yep, so we kick our lone pair down, our double bond gets broken, and we end up with the following valid resonance structure. Now, the reason why we're going through this is because when we look at calculating our bond order, let's take a look at a very specific carbon-oxygen bond. Let's look at this topmost carbon-oxygen bond. And the structure on the left, what's the bond order? 2. And the structure on the middle, what's the bond order? 1, okay. Let me zoom up a little bit. So 2 plus 1. In the structure on the right, what's the bond order? 1. If we divide by our total number of structures, which is 3, that in turn, so for our carbon-oxygen bond order, that gives us 4/3 or a 1.33. So this bond is not quite, it's much weaker than a 1.5 bond, but it's still stronger than a single bond. Does that make sense to everyone? So we have a method of quantifying bond order, looking at resonance contributors. Yeah. So how many bonds do you see in the first structure? 2. Yep, so that's where we get 2. How many bonds do we see in the second? And then in the third? Yep.
So this is just oxygen.
Yep. Or whatever bond that you want to investigate.
Okay.
In this case, I designated the top carbon-oxygen bond, just so that way we have something to look at. Mm-hmm. Though, technically, just as a side note, are all the carbon-oxygen bonds going to be the same? Yes, exactly, because all the structures are equal contributors. Okay, so what I want us now to do is to apply this idea of resonance effects on bond order. And I'd like you to tell me, looking at the structure of benzene, let's try to identify what carbon-carbon double bond is the strongest, and let's identify the carbon-carbon bond order. And we'll do this one together. So, first and foremost, I'm going to look at my structure, and can I draw some resonance structures for this? Yeah, so I can rotate and move over my double bonds in a clockwise manner to generate a new, equally valid resonance structure. Okay, perfect. So we have that established. Now, is there any difference between these carbon-carbon bonds, looking at both of these resonance structures? Are both of these resonance structures equally contributing? So are all the carbon-carbon bonds identical? Yes. So we can't really say which one's the strongest. They're equally strong. The carbon-carbon bonds are equally strong. Okay. Now my next question is, what is the carbon-carbon bond order? And to do this, let's just pick our carbon-carbon bond to look at. Let's look at this top one right here, okay? Doesn't matter which one you choose. I'm just picking one so we have the same reference point. Okay, so looking at this carbon-carbon bond, in the first structure, what's our bond order? 2, yeah. In the second structure, what's our bond order? 1. How many total structures do we have? 2. So what is our carbon-carbon bond order? 1.5. So it's not quite a single bond, not quite a double bond. Does that logic make sense? Okay. So what I want us to consider now is, as the result of resonance delocalization, is this double bond as strong as if it were an isolated double bond? No, it's a little bit weaker, because those electrons are being delocalized over multiple atoms. It's still a stabilizing event, but it does affect your localized bond strength. So what I want us now to do is try another example, except this time I want us to consider and try to answer the question, which carbon-hydrogen bond is the strongest? Now, this question has a lot to unpack, so let's do this one together. So looking at benzene, we have the following 2 resonance structures. We have the following 2 resonance structures at play here. Okay, right? We've agreed upon these resonance structures, right? We've done that in the previous example. Now, what factor is most relevant to the carbon-hydrogen bond strength? What am I asking in this question? What am I trying to get at here? What hybridization? Exactly right, exactly right. So if we look at the hybridization of each of our atoms involved in each of these resonance structures, what's the hybridization in both of these resonance structures? sp2. Yep. And if we've established that all of our carbon atoms are equivalent in terms of carbon-carbon bond order, would you expect all of our carbon-hydrogen bonds to be equally strong? Yeah. So all of our carbon-hydrogen bonds are identical. The key reason why I ask this question is just to get us in the habit of thinking about what is the hybridization, what is the average hybridization based on both of our resonance structures, and in turn, the hybridization of your atom will affect your bond strength. And in this case, all of our carbons have identical hybridizations, all of our carbons are equivalent, so all of our carbon-hydrogen bonds are equivalent. Does that make sense? Okay. Let's try a few more examples. And I want you to take a look at the following 2 structures, and I'd like you to tell me which of the following, which structure has the strongest carbon-oxygen bond. I want you to tell me the hybridization of each atom, and I'd like you to tell me which structure has the shortest carbon-carbon bond. So take a moment to unpack these structures, to draw out the resonance structures for each of these 2 structures, and then take a look at your bond order and your average bond order throughout. So this is the type of question that you potentially see on an exam. When the lone pair gets kicked down, the double bonded electrons get kicked up. So, yeah. Mm-hmm. And try to focus on, instead of doing a full analysis of each molecule, focus on differences between these 2 molecules. Everything going okay? Yep. Yep. Yep, looks good so far. Everything going okay?
Yeah, I was just a little less, starting to draw the resin structures.
Yes, and try to look at differences between them. Because you may not need to draw. When you're starting out, you'll have to draw all of them. But try to think about what happens when you have additional resin structures that you could draw. What happens to your carbon-oxygen bond strength? What happens to the carbon-carbon bond strength? The more those electrons are delocalized. Yes. But try to draw the structures to prove it to yourself first. Yep. So when you kick your lone pair down, the double bonding electrons get kicked up to the atom that does not have the new double bond. So the double bonding electrons get kicked up to the carbon. Yep. Yep, no, that's exactly right. Mm-hmm. Yep. Mm-hmm. Yes.
Like, okay. For some reason, I was thinking over here, but no.
You have it right. Mm-hmm. Everything going okay? So I've seen a lot of resonance structures drawn. And to help us throughout this process, what we're going to do is I'm going to draw out a bunch of resonance structures. And what we're going to do after we have all these structures drawn, if I miss any, let me know. And then we're going to analyze all of our resonance structures to look at our bond order. Okay? So for structure number 1, the first and probably the most obvious resonance structure that I've seen many people draw is you kick the lone pair down and the double bonding electrons get kicked up. So I've seen that a lot. That's perfect. So we have the following resonance structure. And I'm going to keep these with the same ink color for now, just so that way we can start to get to the meat of this problem. Okay, so here's our first resonance structure. Now we could potentially kick this lone pair of electrons. We can potentially move this lone pair of electrons down, breaking our carbon-oxygen double bond. And now we've delocalized our lone pair. We've delocalized our lone pair across into this other pi system, giving us the following resonance structure. Now, there's one more resonance structure that we can potentially draw. And to accomplish that, we can't access the next resonance structure just from here. We can't access it straight from the structure that we've drawn. So we're going to have to go back to our initial structure and make one minor adjustment. So the next potential structure that we can access is going to require a little bit of careful movement of electrons. So starting off from structure number 2, what we're going to do is we're going to kick the lone pair on this topmost oxygen down and break our carbon-oxygen double bond. Now, the reason why I'm showing you this in detail is you do not want to cut corners when you're using arrow pushing. You want to make sure your electrons flow from your lone pair to the final location where that lone pair ends up. Your flow of electrons should be in one direction. Okay, so that in turn gives us one more resonance structure that we can look at. I know it doesn't look like much, but it's really important towards this problem. And of course, now from this new resonance structure that we've drawn, we can of course delocalize this lone pair into the pi system and generate a very interesting looking resonance structure that has a different arrangement for our carbon-oxygen double bond. Now, this kind of problem, and the goal of this kind of problem is to get you to think, what happens when we change the atoms and substituents in our molecule? How does that potentially affect our bond length and bond strength? So these are all the resonance structures for our first molecule, okay? And now what I want you to pay attention to is if we look at the difference between these two molecules, the only difference is we have replaced a carbon with an oxygen. This may seem like a minor substitution, but has a pretty interesting effect on your bond length and strength. Everyone following with me so far? Do those resonance structures that I've drawn match? I saw a lot of those on the papers that when I was walking around the class. So everyone's pretty good on that. Now, thankfully, for the second compound, we don't have nearly as much work to do. So starting off, so for compound number 2, I'm going to use a slightly different color. So starting off for compound number 2, we start off with the following Lewis structure. And of course, we have a lone pair and a double bond. Can we delocalize our lone pair? Can we push our lone pair down? Yes. So let's do just that. We take our lone pair, we kick it down, and we generate an anion. You may notice that if you've drawn resonance structures for your first molecule, you're going to be pretty good at drawing resonance structures for our second molecule. Okay, so here's the next resonance structure on our list. Now my question to all of you is, can we delocalize this lone pair into this pi system? Do we have a lone pair adjacent to a double bond? Yes, so we can delocalize it just like before. And that in turn leads to the following structure. There we go. And that's about it for the major ones. Now, what I want us to do now is to compare. If we think about our total number of resonance structures, let's take a look at our carbon-oxygen bonds, and let's specifically look at the bond order in each of our carbon-oxygen bonds in each of these resonance structures. Okay, so that's what we're doing now. We have our resonance structures. Now we're going to analyze and see in which structure do we see the largest average bond order. So to make things easy, let's start with this bottom structure. So in this bottom structure, I have a bond order of 1 and 2 in my first resonance structure, right? Now, in my second 2 resonance structures, I have a bond order of 2 and 2 and 2 and 1, okay? So on average, if I look at my average bond order, I have 5/3, which is about 1.66. So that's for our carbon-oxygen bond. Does that make sense where I got these numbers from? Now, let's do the exact same thing for our carbon-carbon bond. Let's look at our carbon-carbon bond. So let's do that in a separate pen color. So in purple, we're going to look and we see we have a bond order of 2 and 1, 1 and 1, and 1 and 2. So if we add them up, 2 plus 1 divided by 3, we end up with a bond order of 1.33. Okay, so that's our analysis for our first structure. Does that make sense? Yes.
I'm confused. Where are you getting the bonds again?
So I'm looking at so in the first example, I looked at the carbon-oxygen single bonds. So in the first case, I have a single bond and a double bond, 1 and 2. In the second case, I have double bond and double bond, 2 and 2. In the third case, I have a double bond and a single bond, 2 and 1. So I average the bond order for a given carbon-oxygen bond, and I get 1.66. Yes?
So I saw that you put a box only around a 1 and then.
It's just because they're identical.
Okay.
Yep.
So did you like add those, so for like that structure, did you add that 3 together and then add those 2 together?
Yes. So I was looking specifically at the carbon-oxygen bond on the left, and I added up the bond order in each of these 3 structures. Does that make sense?
Yeah. I get that you added, when I say added, I'm talking about where you pull your 5 from.
Yes,
You have
it's
that
one.
2 in a box,
Yeah.
that 2 in a box.
Yeah,
that 1.
exactly.
But what are you doing with the numbers you didn't box?
That's the other carbon-oxygen bond, and thankfully it's identical.
Oh,
Yeah,
okay,
yeah.
okay. I see what you're saying.
Yeah.
So it's both one in
Yes,
the box.
yes.
Okay.
Likewise, our carbon-carbon bonds are also identical. So as a result, when we look at our bond order, we have a bond order of 2, 1, and 1. Averaged together, that gives us 4/3, which is a 1.33 bond. Does that make sense? Now, and this is where, if you're paying careful attention, you can reduce the amount of work that you have to do tremendously. So what we're going to do in this topmost example is we're going to take a tally of each of our carbon-oxygen bonds, and we're going to look for and think about what happens when we add this oxygen. So what happens when we add this oxygen? Just as a general rule of thumb, what happens when we add additional atoms into conjugation? Yes.
We're increasing the concentration.
Yes. And what happens to our electron density? Is it now spread out over multiple atoms? Just like in our carbonate example, right? We added another oxygen, our bond order weakened because we're distributing that electron density over more atoms. So what we can do in this case is let's now focus just on our main 2 carbon-oxygen bonds. So in this case, we have a bond order of 1 and a bond order of 2. Is everyone following where I got the 1 and 2 from? We have a single bond here and a double bond here. In the second example, we have a bond order of 1 and a bond order of 2. In the third example, we have a bond order of 1 and a bond order of 1. In the fourth example, we have 2 and 2. And in the last example, we have 2 and 1. Let's now just focus on one of our carbon-oxygen bonds. So let's now average out our bond order together. We have 1 plus 1 plus 1 plus 2 plus 2. So that in turn gives us 7. And how many total resonance structures do we have? 5. So 7/5, that's approximately about 1.2. So if we compare, looking at our carbon-oxygen bond, in which structure do we have the stronger carbon-oxygen bond? The structure with the highest carbon-oxygen bond order. Second one, right? Does that logic make sense? Does this analysis make sense? This is really critical since it allows you to assess bond strength, and towards the end of this class, we'll use this to help get a sense of spectral properties, which are based on bond order. Let's now, would someone like to take a guess based on this general trend? When we add an oxygen atom to our structure, what happens to our carbon bond order? Would you expect it to go up or down as we delocalize our electron density over more atoms? Down, exactly. And we can showcase that. So in this first structure, we have 2, 1, 1, 1, 1. So if we add them up, we have, for our carbon-carbon bond, we have 2 plus 1 plus 1 plus 1 plus 1. That in turn gives us 6 divided by 5. That's about 1.2. So we can show mathematically by averaging that our bond order has decreased. Now, this is all approximate. I'm not asking you for exact numbers here on the bond order. The reason being is, are all of these structures equal contributors? No, of course not. But this idea of looking at resonance structures, averaging your observed bond orders to predict and compare the bond orders in 2 different molecules is a critical skill. Does that make sense how to perform this operation? Now, what I want us to do is we're going to apply the same logic to a new example. And what was our takeaway from this discussion? When we add additional atoms to our conjugated system, what happens to our bond orders in general? They decrease. And the reason why they decrease is we're spreading our electron density over more atoms. Does that make sense? Okay. So what I'm going to do now is I'm going to let you loose on this next problem. And I want us to compare the following 2 structures. And this one is much more manageable in terms of the resonance structures that you'll have to draw. I'd like you to tell me which structure has the strongest carbon-nitrogen bond. And I'd like you to tell me which structure has the shortest carbon-carbon bond. Everything go up? Yep. 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 It goes up. Everything going okay? Yep. Good so far. Everything going okay? Okay. Everything going okay? Oh, I would recommend pushing electron density from lone pairs to double bonds. So you can move your lone pair electron density to any atom. Good. Yep. And then the double bond electron density gets kicked up to the atom, not involved in the double. Yep, exactly right. Did it make sense?
It didn't make sense.
Yeah.
So now I'm just assuming right now.
Yep.
Is that fair?
Oh,
If we assume that, maybe because I don't have a double
the
bond.
carbon-carbon. So which stronger in general, single or double bond?
Double.
Double. So you're looking at resonance effects on your double bond order. Yeah. Everything going okay? Yep. Yep. And there are a few more that you can draw, just to help prove to yourself which one's stronger. Everything going okay? Yep. Yep. That looks fine. Yep, that looks fine. Everything going okay? Yep, just don't forget to draw both double bonds. Like in this one, don't forget to draw the second double bond. Yeah. Yeah. Yes. Yep. Yeah, but the lone pair ends up on the atom, not involved in the new double bond. Oh, so in general, your arrows are going to go in one direction. So the arrow will go from this double bond to the carbon atom. Yeah. As you form a double bond, the previous double bond breaks. Yep, exactly. Everything going okay?
Yep. So as a result, you can think of it as your double bond electron density is now distributed over 5 atoms versus a double bond electron density. So so essentially what's going on here is you have 6 electrons over 5 atoms. In this case, you have 4 electrons over 3. 6 over 5 is less. So let's now take a look at the following structures. And just one rule that I like, one heuristic that I use just as a first look, I like to take my number of electrons and divide it by my number of atoms. And that gives me a sense of the bond order, approximately. It's not exact, but it's a nice little shortcut that I use when I'm looking at molecules to get a sense of resonance effects on bond order, right? So let's show how this would work. So looking at this structure, I have a total of 6 electrons in my pi system, right? My 2 double bonds and my lone pair. And this is going to be spread over a total of 5 atoms. Compared to the structure on the right, I have 4 electrons distributed over 3 atoms in my pi system. And that gives me about 1.33 versus about 1.2. This is not an exact calculation of bond order, but what this calculation helps demonstrate and helps you get a sense of is the relative amount of electron density distributed in a given bond in a pi system. Does that make sense? So based on this idea, which bond, which system will have in general stronger bonds, more electron density shared between our atoms? The one on the right, exactly, as we'd expect. The less delocalized our electrons are among multiple atoms, the stronger our individual bonds. So then, as a consequence of this, if we just had to predict a priori, what would we predict for the structure with the strongest carbon-nitrogen bond? Which structure would we predict to have the strongest carbon-nitrogen bond? Yep, and which one would have the shortest carbon-carbon bond? The one on the right, right? Because strong bonds are short, right? So, but let's justify our answer. I hate heuristics because they're useful, but until you actually go through and you draw out the resonance structures, for all you know, that rule just doesn't actually work. So let's now take a look and let's draw out some resonance structures. The first of which we can draw by kicking our lone pair. Oops, one moment. The first we can draw by kicking our lone pair down, and in turn we break our double bond. So the first major resonance structure that we can draw contains a nitrogen-carbon double bond and a lone pair centered on carbon. We can draw one other major contributing structure, and this time we're going to kick this lone pair through our entire pi system. So let's follow this. I'm going to kick my lone pair down, and my lone pair goes up towards nitrogen. That's what we can do. Instead, if you want to showcase the movement of electrons throughout your pi system, instead we're going to kick our double bond to the opposite side of our carbon-nitrogen bonding system, and then turn, we're going to kick our double bond up to generate a lone pair on carbon. That in turn gives us the following resonance contributor. Now, of course, these are minor contributors, but nonetheless, they do affect our bond length and strength. Does that make sense to everyone? Now let's handle our simpler structure. Let's handle our simpler structure. Looking at the following system, The main distinction between these two systems is that we have less total conjugated atoms. So when we draw out our resonance structures for the second structure, we can only really draw one remotely major contributor. Sorry, I'm just filling in my formal charges. Okay, now that we have all of our resonance structures drawn, let's test our theory. Let's test our theory. Now, what I want us to do is in red, I'm just going to make a note of my carbon-nitrogen bond order in each of these structures, okay? So first, I see 1 and 1. Next, I see 1 and 2. And in the third structure, I see 2 and 1. So if I average together, if I average out my carbon-nitrogen bond order, let's just look at one set of numbers for one carbon-nitrogen bond. I see an average bond order of 1 plus 1 plus 2, right? So 1 plus 1 plus 2. And how many resonance structures have I drawn? 3. So then, divided by 3, that gives me a bond order of 1.33. Did we miss any resonance structures here? It looks like we covered them all. Let's now look at our carbon-carbon bond order. Let's do that in a slightly different color. Let's look at our carbon-carbon bond order. So, looking at our carbon-carbon bonds, I see a bond order of 2 and a bond order of 2. In the second structure, I see a bond order of 2 and 1, and then 1 and 2. So averaging out, 2 plus 2 plus 1 over 3 gives us 1.66. Everyone following so far? Now let's assess the carbon-nitrogen bond order in our second example. So I see a carbon-nitrogen bond order of 1 in the first resonance structure and 2 in the second. So 1 plus 2 divided by how many total resonance structures? How many do we have in the second example? 2. And that in turn gives us a carbon-nitrogen bond order of 1.5. Let's do the same thing for our carbon-carbon bonds. So we see a bond order of 2 in the first example, 1 in the second. 2 plus 1 over 2 gives us 1.5 for our carbon-carbon bond order. So looking at, let's take a look at these really quickly. Let's see if we made any mistakes. So everything looks good from here. So then my question to all of you is, which of the following structures would we expect to have the strongest carbon-nitrogen bond? In which structure do we see the largest bond order for our carbon-nitrogen bond? Which one? The structure on the top or the bottom? Bottom, yep. So we'd expect the structure on the bottom to have the strongest carbon-nitrogen bond. Looking at our bond orders for our carbon-carbon bond, however, which of the following structures has the largest bond order for the carbon-carbon bond? The top structure. Yeah. So although this heuristic that I showed you is useful, it is not accurate for every single system. That's why you have to draw out the resonance structures, count and average your bond order, and then compare. Does that make sense to everyone? So we'd established that the bottom structure has the stronger carbon-nitrogen bond, and the top structure has the shorter carbon-carbon. Yes? Yeah, the larger the bond order, the shorter and stronger your bond. So you should be able to do an analysis like this on your exam, and you've seen some of these on the pre-lecture quizzes already. With that, we're all set for today. We'll continue on with acid-base chemistry next session.